Okay. What I want to do with this, just to kind of explain to you in behavior and explain to you that one of these terms up there, it's the reason we call it the leading term, or sometimes we call it the dominating term, why it gets that kind of descriptor, okay, and why we describe it that way or call it that. I just want to rewrite this. I don't want to change the function description. I just want to change the way it looks, okay? So can I divide out anything that I want to of that from that function? Yeah. When you do it to both sides. Well, I don't want it to both sides. Think about it. Let's say, can I divide everything here by 2? As long as I leave that 2, so as long as I leave that 2 right there, can I? Yeah. I can pull out like a GCF, right? Okay, now that thing doesn't have a GCF. There's not a greatest common factor for all of those things, but I can pull out any factor that I want to. So let's do this. Let's divide out that leading term. Okay, so I'm going to rewrite this so we have a 5x to the 5th out here. Okay, now I'm going to rewrite this in each one of these terms. So this one's going to be, the first term is 5x to the 5th, and when I divide out or factor out, it's division, right? So we're going to go through and rewrite each one of these terms over 5x to the 5th. Okay, so give me a minute to do this. Okay, so if I had f of x looking like this, that says the exact same thing as the top black line. Okay, if I multiplied that 5x to the 5th I have on the outside, all those denominators cancel, right? And I'm just left with the numerators, and which is exactly what we had in the black. Now I want to go through and actually reduce these. Okay, so we have 5x to the 5th up front. What's this reduced to? 1. Plus now I'm going to have 4/5. But where's the x? Shows on the bottom, right? Okay. This was going to be 7/5. Where's the x going to be? The bottom, and it's x squared. It's going to be 2/5 x cubed on the bottom right. So because my divisor had a power that was bigger than all my numerator's powers, all my variable parts are going to be left on the bottom, right? Okay. That says the same thing as what I started with, correct? Okay. Now, in behavior, what in behavior is the idea that x is getting very, 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 very big. Does that make sense? Okay. So I'm going to evaluate this thing at a very, very, very large number. Okay. Let's ask that. We're going to put in there a number for x that approaches infinity. Okay? Choose a very large number. If I choose, and really, guys, if you choose, when I say a very large number, like a billion, you guys probably think it's a large number. If I give you $1 billion, that's large. But $1 billion is nowhere close to being big in comparison to a Google, okay, or a Googleplex. Does that make sense? Okay. $1 million. If I give you all $1 million, you guys would say that's a lot of money. That's a big number, right? $1 million is nowhere close to $1 billion. Okay, like 1 million, if you see about in regards to seconds, I think it's like 7 years or something like that. Okay, a billion is like 33 years, okay, in seconds. So that's it's all relative, I guess, when we say a really, really, really big number. So let's choose, let's say that I choose $1 billion. Plug $1 billion here. 5 times $1 billion to the 5th. Let's take $1 billion, 9 zeros, and multiply that by itself 5 times. Is that a really, really big number? And multiply that by 5. Is that an even bigger number? Okay. Just keep that in mind. When I plug in $1 billion here, obviously there's nowhere to plug it in there, right? It's just 1. When I plug in $1 billion here, what's 4 divided by 5 billion really close to? Zero. If you took if I give you $4, say, divide that out from 5 billion people, basically everybody gets nothing, right? Okay? So that thing, when X is really, really, really big, that thing is actually 0, okay? Or very negligible, okay? Not much more than 0. Okay, think about that 7 over 5x squared. Now, X is a billion, but now I square it, so I have 9 zeros, now I have 18 zeros in the bottom, times 5. 1 divided by 5 followed by 18 zeros. What's that number pretty close to? 0. Does this thing go to 0? Just happens a lot faster. Does that make sense? Okay? Because now I'm taking that 1 billion and cubing it. So now think about all those zeros. Multiply by 5. 2 divided by a huge number is 0. That's going to go to 0. That's going to go to 0, right? So what is 1 plus 0 plus 0 plus 0 plus 0 plus 0? 1. So inside those parentheses, when X is really, really, really big, inside that parenthesis, all we really have is the value of 1. Meaning that 1 came and basically tells us that stuff really isn't important. Okay? It's negligible. It's creating a very, very small number in comparison to that one. Does that make sense? That one's still out there. It's about 5x to the 5th out here. But when X is really big, 5x to the 5th is a really big number, right? Is it positive or negative? It's positive, okay? So X to the 5th, so it's an odd degree right now, okay? But we're seeing that as X goes really, really big, this algebra tells us that our Y value got really, really big. So as X is going to infinity, Y is going to infinity. Does that make sense, everybody? As X got really, really negative, think about this. X gets really, really negative, really, really big in the negative direction. This is still 0. Does that make sense? Okay? This still goes to 0, still goes to 0, still goes to 0, still goes to 0. They're just on the left-hand side of 0. Does that make sense? Okay? But they're all very negligible, so 1 plus all of those come together is still just essentially 1. Okay? It might be like 0.999999999. That's me, 9, you can say. Okay? But now, if X was a negative value, what's a negative value times itself 5 times? A negative. So if I take 1 billion and multiply it by itself 5 times, I get a negative number that is much, much, much bigger than a billion, right? Multiply by 5, it's still negative, correct? So you see here then, as X is going to a negative value, your Y values are going to a negative value. Okay? Negative infinity. As X goes to negative infinity, Y goes to negative infinity. That's the idea of why we call it a leading term or a dominating term, is because it dictates the end behavior. Okay? It is so much more important than the other terms. And that's just, I used X to the 5th, and I wanted to have a couple different things inside these parentheses. But the same thing happens when we talk about X to the 1st and X cubed. Okay? Think about X to the 1st. If I have 2x plus 1, okay? You guys know that graph probably looks something like that red line, right? Okay? Well, if X goes to infinity, let's say X is 100 million. Okay? If X is 100 million, does adding $1 to 100 million really matter? No. Okay? Or doubling it first and then adding 1. Doesn't really matter. That 1 plus 1 isn't doing anything for me in the long run. Okay? Now, it does do stuff in the middle of the graph, okay, down close to the origin, relative to the origin. That plus 1 is important. But in the long run, in the end behavior of my graph, the 2x is what's dominating. Okay? Is that okay with everybody? All right. So, and I don't know if did I show you guys yesterday the behavior of even and odd degree functions, showing you how we got time, so I add x to the nth power and show you when n is positive. Let's just change these so we don't get any of those fractional exponents. Start at 1, go to 12. Increments of 2. All right, so that's a linear function. That's a cubic, right? Quintic, 7th degree, 9th degree, the 11th degree. I showed you this yesterday. Are they all kind of the same? Even that one, in regards to the end of it, is the same as that one, right? So an odd degree, we see as the x's go to the right, as the x's get bigger and bigger, the y values get bigger and bigger. So x, and just the higher the exponent just tells us that happens quicker. Okay, if I take 2 and raise it to the first power, I get 2. Take 3, raise it to the first power, I get 3. So the y values are increasing kind of steadily here, pretty slow. If I go to the third, now I take 1 and cube it, I get 1. But 2 and I cube it, it's going to shoot up to 8, right? So at a small x value, I'm already at a pretty large y value. 3 is going to shoot up to 27, okay? So it shoots up real fast. Well, then if I go to the fifth power, okay, well, 3 to the fifth is, 3 times 3, was that 81? No, it's 2, 81 is 3 to the fourth, isn't it? Okay, so 243. So at a value of 3, we're already up in the 200s, okay? So the higher the exponent just means the y values shoot to infinity faster than what they did with a lower exponent. Does that make sense? Okay. But is the end behavior still the same? Yeah. Still go to positive. As x goes to positive infinity here, as x is going this direction, y is going up. Y is going to positive infinity. It just gets there faster the higher the exponent. Okay. The higher that leading exponent. So all of our odd degree functions are going to have that similar end behavior. Okay. When the number out front is positive. What if that number out front is negative? And I'll just make it 1 to 1, by 2s. Okay, if it's negative, do you see how the end behavior just flips? Because it's a horizontal, it's an x-axis reflection, isn't it? So if I know what my end behavior looks like for x to the third, or x to the seventh, or x to the fifth, when I know with that coupled with a transformation, a reflection, I should know then the end behavior for negative x to the seventh, or negative x to the fifth, or something like that. Okay? Because it just ultimately flips the end behaviors. Now, if I talk about the fourth degree, second degree, sixth degree, those types of functions, we call them even degree functions. Let's make A positive. As x is going to the right, y is going to positive infinity, right? As x is going to the left, or negative infinity, y is going to positive infinity. Is that the same for all of these? Right? And if I make A negative, now as x goes to positive infinity, y goes to negative infinity, right? It just flips the y. So understanding that relationship, I think, helps us with our understanding our end behavior when we look at a function. Our goal is to ultimately, guys, be able to look at something like that and automatically know, because of the negative 2x to the fourth, when I move x to positive infinity, my y value is going to negative infinity. As x goes to negative infinity, my y value goes to negative infinity. That's our goal when we look at functions, and to know that instantaneously without having to graph it. Okay? Now, when we look at these rules here that I've kind of set up, I just want to show you what those dotted lines mean. Okay? And we'll get into a lot more detail of this throughout the rest of this section when we do end up finishing it. If I look at, let's just say, a fourth degree polynomial. Okay? So what I've just done here, and I'll show you the polynomial down here, object G. So that there is my polynomial. Okay? And these things just allow me to change the coefficients. So you see those coefficients change on there. If my coefficients are all 1, obviously that's the shape that I get. But if they're all 0 except for my A, it gives me that x to the fourth curve, right? Okay, so my x to the fourth curve can look like that. My x to the sixth can look like that. My x to the eighth can look like that. The only thing that happens is that they get a little bit more kind of squared off down there at the bottom towards the x-axis, the larger the exponent 4, 6, 8 becomes, okay? But the behavior that happens in between here, okay, so let's see. If I change the A value, change the B value a little bit, okay, you start to see maybe a different kind of behavior around the origin, right? Now, I say around the origin, that's relative, okay? You know, we could say that a million is around the origin if I compare it to a billion or to a Google. Does that kind of make sense? So closer to the I call it the middle or the interior of my graph, we can have some different behaviors occurring, okay? Depending on the type of coefficients I use for the remaining terms in my polynomial. But notice that the end behavior is still the same, isn't it? As x goes to positive infinity, y goes to positive infinity. As x goes to negative infinity, y goes to negative infinity. No matter how I change these, okay? No matter how I change them, so maybe I can make it look like a little bit of a W, okay? It still has the same end behavior, right? All right. Now we could, if we had time, I've never done it, but I'm assuming that we can investigate and say, okay, when I have a fourth degree polynomial, what does changing the coefficient of the x cubed term, what does it impact? Because you can see that as I change that, as I change the B term here, we're kind of seeing just part of the graph change, right? And we're not seeing, you know, this left-hand side really isn't changing too much. It is changing, but not extreme as the right-hand side is. So I'm assuming that we could investigate and say, what does that coefficient contribute to the problem, okay, to the graph? But we have essentially those varieties of curves that we can see from a fourth degree. They can look parabolic. Okay, it kind of looks parabolic. If I was able to get these all back to zero, it looks parabolic. It's not a problem, but it looks kind of that way. We get something that has ultimately three. If I ask this thing to find its extremums, see how it has three, okay? Or we could have the potential of having only one extremum. Does that make sense to everybody? Okay. So there's a variety of things that we could have there, okay? And later on we'll talk about the fact, because this is a fourth degree polynomial, the fourth degree, the maximum number of extremum I could have is 3, okay? Because if I was able to have 4 extremum, and I'm going to call them turning points, okay? Would you guys agree A is a turning point for that curve? Changes from increasing, decreasing, decreasing, increasing, okay? If I were to have 4 turning points, there would be 1, B would be 2, C would be a third one, and then a fourth one would be kind of like that, right? Well, if I have a fourth turning point, now my curve is decreasing, and I don't have any more turning points. Will that match up to the end behavior that I'm supposed to have for next to fourth? No, okay? So I can only have, in this case, a maximum of 3 turning points. Can I have 2 turning points? Can I just have 2 turning points? So if I go 1, A is 1, B is the second one, can I max out at 2 turning points? No, I got to have one more to match up my end behavior, don't I? So a fourth degree polynomial can have 3 extremum or 1 extremum. Okay, has to have those kind of relations, and those are things that this course is getting us to investigate and to be able to recognize and understand. That when we look at this equation, we should be able to set forth right away. I'm going to have a potential of 4 zeros. I'm going to have a potential. I know my end behavior. We're going to talk about that. I have a potential of a maximum of 3 turning points, or maybe just 1. Okay, and I've got that kind of built into my head, those potential characteristics, before we even set forth and start trying to solve for things like x-intercepts, y-intercepts, and graph this thing. Okay, so they're all relations. They're all characteristics that we're interested in. Now a 6-degree polynomial, I think I've got a 6-degree here, okay? You can see that a 6 degrees, it's the stuff in the middle there, in the interior of the graph, it's doing some weird things, right? But is the end behavior the same thing as what x to the 4th was? Same end behavior as the x squared was, okay? But now we see, I would ask it to, seriously. Okay, to find those extremums, we see we've got 5 now, right? The power was 6. Now we have 5 maximum extremes. Because if I only had 4, I'd go A, B, C, D, and I'd keep going through D. I wouldn't turn back up, right? Okay? I got to turn back up to match up my end behavior. And why do we have to match end behavior? Because of that algebra we did earlier where we factored out that leading term, right? Okay? That algebra validates or confirms that we have to have a positive y value as that's getting very, very big. But could I have maybe only 3 extremums? Is that going to make sense? So we're going to have 5 or 3, or what do you think the other one is? 5, 3, or 1. Okay, because my 1 would be kind of the most basic version. So there's a situation where we got only 1, right? That makes sense? This point right here, okay, because it is kind of a little bit different than what we've seen. That's how we call it an inflection point, okay? Basically meaning that from the left of that, we are decreasing, but we flatten out. But then after that, to the right, we keep decreasing, right? So we call that an inflection point. But that would be kind of the most simplistic version of our 6th degree having 1 minimum value. Okay. When we talk about odd functions, odd degree functions, same thing happens. We got to match the end behavior. Okay, so here is a odd degree function. Okay, is it its 5th power? Is that matching the same relationship that we see for end behavior of an x to the 3rd or of just an x to the 1st, right? Okay, but on the interior, we've got some weird things going on. We could have, because x to the 5th, I ask this thing for some extremums. Okay, right now it just shows me 2. If I start to maybe, there we go, manipulate this, and again, having a little bit better of an analysis of what the coefficients of the other terms are doing for us. There we go. So it's 5th degree. Do we see kind of the ability to have 4 turning points? If I had another one, we would be not mimicking the end behavior, right? Okay. But as we saw those 4 develop, we also had the kind of understanding that we could have at some point 2, right? And then, and this is all because I was going to make these sliders a little bit bigger. Let's go to 50. We can see that, and just kind of show you, I mean, just changing those coefficients kind of makes a little bit weird things going on here, right? The end behavior is still the same, isn't it? X goes to the right, Y still goes to positive, X goes to the left, so there's a negative infinity. We can mess around with that enough to eventually see these 2 points come together, and we just have essentially a potential of no turning points, no maximum minimum. Does that make sense to everybody? Okay. And we'll define that. I'll give you a rule that dictates how many turning points that we can have, but hopefully you're seeing by the patterns. If I gave you a 12th degree polynomial, Anybody want to guess how many turning points you're going to have at most? 11. Okay. And then can I have 10? No. I could have 9 though, right? So I subtract 1 to get the most I could have, and then continue to subtract 2 away from that, and it'll give me my potential. Okay. And those are things that we'll definitely write down and investigate. I told the last class guys, there's a lot of stuff right here, I think, in this picture to try to memorize. Okay? And you've heard me say this before, don't memorize things, because what's your memory do to you at some point? It's going to fail you, right? Things are going to fade. Okay? If we know that, hopefully, when we learn something, we can kind of learn it in a manner that counteracts that fading. No matter how we learn it, though, it's probably going to fade to some degree. All right? I gave them an analogy earlier. Those filing cabinets, when I got them, they had like 70 years worth of papers in them because they were just passed down from math teacher to math teacher, and nobody ever threw anything away. They were packed, couldn't move them. They were heavy as crap. I took all that stuff out and threw it away. Okay, I didn't need that stuff. Okay, but if when they were filled and I had to go look for something, with all those papers and files in there, it's really hard to find. Does that make sense? But if I reorganize things, okay, and I basically take things out that I don't need, and I put in there maybe 10 files. Now when I'm looking for something, I can go find it, and it's easy to find, right? That's how you want to structure your mind. Your mind's a filing cabinet. Don't memorize all of these things. Don't memorize every single picture, okay? Maybe understand what x to the first looks like, or x cubed looks like, and understand what its in behavior is. And then understand that when I have x cubed and the in behavior is this, okay, that this graph here is simply, when A is negative, it's a x-axis reflection, and doesn't that just flip the in behavior that you had here and create in behavior here? So developing those relationships allows you to not have to memorize maybe 4 pictures and 2 in behaviors for each of those pictures, but remembering 1. Okay, remember 1 in behavior and then link that with what we know already about transformation. So developing those relationships helps you categorize things, store things, file things in your memory a little bit easier. So it's easier to recall, easier to apply, because there's not so much crap up there in your head anymore, right? Okay. Anybody take psychology? You guys talk about that at all? Like how you structure your thoughts, structure your storage of ideas? We're continuing with this stuff tomorrow. 3-2 is open. It's not due tomorrow. Okay, so do not worry about it being due, even if I don't turn the due date off until later.
Don't plan on